Okay, good afternoon, everyone. Today we'll look at BJTs, bipolar junction transistors, by far the most important device in semiconductor devices. This was actually the first solid-state semiconductor device that was presented to the world. This happened in the late 1940s by three scientists who were working at Bell Labs: Walter Brattain, William Shockley, and John Bardeen. And can't remember which one. All three of them won the Nobel Prize for their discovery and presentation. Um, one of them, gosh, I knew this, I forgot. One of them went on to UIUC, professor in chemistry or physics, no, physics, and he won a second Nobel Prize, which is very rare. There's only a handful of people who ever actually won two Nobel Prizes. One of them was one of the most famous women to ever win it, Marie Curie. She won two. She had a daughter who won one Nobel Prize, and then her son-in-law also won a Nobel Prize. It's a family of overachievers. But I find that kind of history fascinating. So if that's something that interests you, you should definitely read up about it. Anyway, so BJTs, bipolar junction transistor. Let's take a look and begin. All right, so so far we have looked at devices or semiconductor devices with just two terminals. Two terminals, one junction. So you have P-type material and an N-type material. We bring them together. It's two separate materials, two separate terminals, one junction, one PN junction, right? Then in this chapter, we're going to look at multi-terminal devices, but multi-terminal in the sense that is just more than two. For the most part, we'll focus just on transistors, which are three-terminal devices. And then there are MOSFETs, which are four-terminal devices. There are SCRs, silicon control rectifiers, that are four-terminal devices. There are triacs that are four-terminal devices. There are even some five-terminal devices, which is not something we're going to go very deep into. For the most part, we'll restrict it to transistors. And transistors, again, um, we keep our discussion for 315 limited to the systems and application, right? So, sorry, not limited system. Our primary goal is systems and application using these devices. So we restrict our discussion to the most fundamental of things. And once we are done with the fundamentals, then we move on to application. And so that's what I want to cover today, because in lab 3, that's what we're going to do. We're going to take a BJT and we're going to create an amplifier, different amplifier circuits. Okay, so multi-terminal devices. No matter how many terminals a device has, 2, 3, 4, 5, all the fundamental laws still apply. We have KCL, we have KVL, node voltages, node voltage analysis, all of those still apply, right? So if you have a multi-terminal device, like a BJT, which has three terminals, you can have three currents. In a PN junction, we have two currents and two voltages. We can label them as all going in, because if you're looking at it as a black box or a sealed box, we have no idea what's inside the system. We only see there are three terminals. We don't know where the current's going in or out, so we just pick reference directions. All three of them are just entering the device, which of course is not true. Law of conservation of energy applies. If one or two currents are going in, then the third current must be coming out, which is what happens in a BJT. Okay, we have two currents entering the device and one terminal current comes out. Well, actually, it happens both PNP and NPN transistor, but we'll take a look at it. Also, the diode equation that we looked at, ID, diode current, is equal to IS into E raised to VD over VT. That still applies, okay? Because it's still a PN junction device, right? So a transistor symbol looks like this. Okay, three-terminal device. And we'll cover everything bit by bit. But let's for a moment, just for a few moments, let's think back to when I was talking about vacuum tubes. Remember, I talked about the first vacuum tube. It had two electrodes, an anode and a cathode. So two electrodes means diode, right? Currents flowing between the cathode and the anode. But there was no way to control the flow of current internally, right? We can control it externally by just changing the supply voltage, but we could not control it internally. So introduce a third electrode alongside the beam. When you insert the third electrode, now you can control the flow of current. Well, the transistor is the solid state version of a vacuum tube triode. Current flows from the collector to the emitter. Sorry, not, I should have. So the two terminals are known as collector and emitter. And then we can control the flow of current via the base terminal. So those names are listed here. You have the collector, emitter, and the base. Okay, collector, emitter, and base. Okay, so far so good. This right here is just the SPICE description of a standard bipolar junction transistor. It's 2N3904. The lab kit might have 3904, it might have 2222. Almost equivalent. Okay. Saturation current, the collector current, they all are the same or similar to what we already learned for the diodes. Okay. Now, before we get into the BJT and see how and why it works, let's reflect back on the diode, specifically the two modes of operation, forward bias and reverse bias. Okay. Because when we create a circuit from a BJT, if you try to analyze a BJT, it actually does not simply function as two back-to-back PN junctions. Right? We say it's a three-terminal device. That means it's made out of three separate semiconductor materials. So BJT can be made out of, that made it easier. BJT can be made out of, can be made in two different ways. We have three separate semiconductor materials. So if we have a N-type material sandwiched between two P-type materials, we get a PNP transistor. If it's a N-type material sandwiched between two P-type materials, we get a PNP transistor. Okay, NPN and PNP. So if you look at the structure of a transistor, what do you think? It's two back-to-back diodes, right? It's two back-to-back diodes. So it's two back-to-back diodes. You either forward bias, if you reverse bias them, there's nothing going to happen, right? Reverse bias junction, very small, limited current flow. But if you forward bias them, you have large amount of current flowing through the junction. So in both cases, excuse me, in both cases, NPN as well as the PNP transistor, if you forward bias both the junctions, what do you expect to happen? Right? You'd have current flowing in, and you'd expect, so in a PNP, the expectation would be currents flowing in this direction, and it'll flow out in this direction. Or if it's an NPN transistor, we'd expect it to come in this way and then flow out the other way, right? Two back-to-back diodes. But it does not function in this manner. And the reason is the physical construction of the BJT and the doping profile of each one of these sections. So we have three sections, PNP and NPN. The doping profile is very different, and the size is also very different. Okay, they are not equal as you would expect in a PN junction diode. And those are the two main reasons why a BJT would not function as a normal as two normal PN junctions. I mean, we're gonna go into detail and look at everything. All right. So we have we have a PNP and an NPN transistor, right? Now, if you have a diode, we have both electrons and we have holes, right? When you forward bias the diode, electrons are crossing over from the N side, holes are crossing over from the P side. They're crossing over the junction and current starts flowing. They recombine and the current starts flowing. So the total current in a diode in a PN type material is a result of both electrons as well as holes. Same thing for NPN and a PNP transistor. Hence the name bipolar junction transistor. The junction just refers to as two junctions. The bipolar refers to the two polarity of the charges. Two polar opposite charges, positive and negative, electrons and holes and electrons, and hence BJT. Diode also has the same, but because diode nomenclature carried over from the vacuum tubes, it came to be known as diode. This came to be known as a transistor. Okay. All right. So these three terminals, the emitter terminal can control the flow of current as well as conduct a large amount of current. The base terminal cannot conduct a large amount of current. However, it can control the flow of current. And the collector current can conduct a large amount of current, but it cannot control the flow of current. Okay? Cannot control the flow of current. The currents that's flowing between, let's forget about current, but controls the movement of the charge carriers, which essentially, of course, results in control of the current, but it controls the current, hence the voltage would also be controlled. But since we are talking at the fundamental level about movement of electrons and movement of holes, and when electrons and holes are free to move, they are transferring energy, we say current is flowing. So for explanations, and we always refer to it as controlling the current flow. Okay, so if you look at the polarities of the voltages that are provided here, you see that this is a NPN and this is a PNP transistor. Now, a quick note, the operation of both transistors is exactly the same. There's no difference. It is exactly the same. The only difference is that in an NPN transistor, electrons are the majority carriers, and in a PNP transistor, holes are the majority carriers. Okay. So for discussion purposes, we will use NPN transistors. NPN transistors are more popular for the simple reason being that electrons have higher mobility than holes. Okay. So transistors, NPN transistors, with the same equivalent doping profile and the same equivalent design geometry, NPN transistors would be faster than PNP. Because electrons are free to move anywhere. Holes can only move into localized spots. Okay, so if you look at the polarity of the voltage here, what do you see? You see that the base, this is an NPN transistor on the left. NPN. It's an NPN, and this is the base terminal. This is the collector, this is the emitter. And the base is plus, emitter is minus, meaning the base voltage or potential is higher with reference to the emitter. So is that junction forward bias or reverse bias? You had a question? Well, that's where I'm leading to. So you answered that question. Is it, what mode of operation is it? Forward bias, right? The base is higher than the emitter, and it's an NPN transistor. In a PNP transistor, the base is lower than the emitter because, again, it's a PN transistor. Okay, so the base emitter junction is forward bias. Now, as I pointed out with those arrows, if that junction is forward bias, we'd expect large number of electrons from the emitter to flow through, large number of holes from the base to flow into the emitter, and it would just function as a normal diode, right? But what we see here is that the collector, it's an NPN transistor, collector is at a higher potential than the base. So if the collector is at a higher potential with reference to the base, that junction is it forward or reverse? Very hesitant questioning, reverse. Fundamental diodes, fundamental PN junction. If positive voltage, if anode P-type material is higher than the cathode, which is the N-type material, it is forward bias. If it's opposite, then it's reverse bias. So the collector base junction is reverse bias. Okay, collector base junction is reverse bias. But if you reverse bias a PN junction, we would not expect any current to flow through, right? You would not expect any current to flow through. Yes, right? Because reverse bias, only minority carriers are flowing the junction. Minority carriers are very low in number. So only the reverse saturation current is flowing through that PN material. So if you want to use the transistor, those are the two questions that arise, right? Those are the two questions that arise. So if it's normal PN junctions, you apply forward bias to the emitter and the base, you'd have large number of electrons crossing over into the base. Current will flow out of the base. Nothing will go to the collector. And collector base junction is reverse bias anyway. So you would say that this junction is on, this is off, and all of the current is just coming from the emitter and the base. That's it. Collector is no longer involved, right? But that's not how it works. The current is actually flowing from collector to the emitter. That must mean that the electrons have to go from the emitter into the collector. Electrons must flow from the emitter to the base to the collector. Then we say current is flowing from collector to the emitter, right? So those are the two questions. So to answer those questions, let's look at a brief look at a forward bias and reverse bias PN junction. What happens in a reverse bias PN junction? We have, this is N-type, right? So N-type, we are applying a positive voltage to N-type. N-type has electrons as the majority carriers. P-type material has holes as the majority carriers. So holes are the majority carriers. Electrons are the minority carriers. And here electrons are majority and holes are the minority carriers. Okay. Again, reverse bias PN junction. What happens? Positive and negative charges, external electric field attracts the electrons and the holes from the N and P type. So the depletion region expands, right? Because they're pulled away from the junction. But what happens to the minority carriers? Minority carriers are pushed towards the junction. If they are close to the depletion region, they're pulled into the depletion region of the electric field. Now they can combine with the holes. Holes are coming from one side, electrons are coming from the other side. And in reverse bias, current starts to flow. But that current is very, very small because the number of minority carriers is very, very small, and it quickly saturates to a certain level. Hence, we call it the reverse saturation current, IS. It is solely due to the minority carriers, right? That's what happened. That's what happens in a reverse bias PN junction, which is what we looked at in PN junction diode. Is everybody with me so far? Okay. So reverse bias PN junction, you have minority carriers that are crossing over the junction. They are now swept away on either side of the depletion region. They are pulled into the depletion region and current starts to flow. So put a pin in that point. Reverse bias, minority carriers are free to cross the junction. Current flow results because of minority carriers. Forward bias. In forward bias, you're applying positive and negative to P and N type material respectively. So the carriers are now pushed towards the junction. There's a barrier, the depletion region barrier. Electrons and holes acquire sufficient energy on either side of the depletion region, and they can cross over into the depletion region, and then they diffuse through. Right, so current starts flowing. Electrons flowing in one direction, holes flowing in the other direction, recombination occurs, currents flowing through, everything's good. That's forward bias. So now let's put it all together. NPN, okay, we are discussing NPN, okay? The actual construction is going to look something like this. And this is, again, just a illustration model. In real life, when we actually create these, you'll remember the silicon wafers I brought, right? So we're looking at it from the top. This is neither the top nor the side view. This is just an illustration, okay? What happens is, instead of like 3 equal parts, the base is actually very, very thin compared to the collector and the emitter. That's the first key thing. Physical construction, physical design is such that the base is very, very thin. Okay. When we actually fabricate this, we have, like, you're fabricating from the top of the wafer. So if I'm looking down from the top, the collector is the biggest, then there's the base inside, and then there's the emitter inside the base. Okay. The emitter could be deep, but the surface area is smaller than the base. And the base, when looking from the side, is very, very thin. Very thin. Okay. But the collector is larger than both. Okay. Collector is larger than both. So this is the collector. That's the base. That's the emitter. And we are looking at an NPN transistor. What are the majority carriers, or what is the majority carriers in the emitter? Electrons, right? So large number of electrons, heavily, heavily doped. Okay. And that's the second key point, the doping profile. The emitter is the most heavily doped of these 3 semiconductor materials. The base is very thin and it's lightly doped. And the collector is the biggest and it's even lightly doped or more lightly doped than the base. In general terms, the doping is like this. Emitter doping is higher than the base, which is higher than the collector. The heavily doped, very heavily doped, lightly doped, or even more lightly doped, that is all relative. Okay. We could say heavy doped, but with reference to what? Well, with reference to the collector. And then we say very heavily doped, meaning it's with reference to the base. So that's what these very heavily and lightly and extra lightly means. Okay. The emitter doping is the highest, the base is far lower than the emitter, and the collector is even lower than the base. And that's the second key point of why the BJT works the way it doesn't work the way as two normal PN junction diodes. Okay. So you remember that pin that I asked you to stick in the reverse bias? Let's take a look at the forward bias first. You have the base emitter junction. We forward bias the base emitter junction, plus minus. What happens? All of the electrons cross over. Oh, left side. Electrons cross over into the base, right? So we have these electrons that are arriving in the base, all of them. Now, when electrons cross over a depletion region, what happens? It recombines with the holes. We say current is flowing, and holes are crossing over into the other side of the depletion region, right? So there are a number of holes here. Recombination occurs, and base current starts to flow. But it's a party in the base, and there's a huge crowd of people that have arrived. Now, they're all crowded into a very small space, and they're hanging around with nothing to do. Okay? But the electrons, what kind of carriers are they in a p-type region? They're minority carriers. So now we have increased the number of minority carriers that are available in that base region. And if now we reverse bias the base and collector region, those minority carriers are free to cross over the depletion region. Again, electrons have arrived from the emitter into the base region. Because the base is very thin and it's much lightly doped than the emitter region, there are fewer number of holes available than the number of electrons. A very small portion of the electrons from the emitter will recombine with the base holes. Current starts to flow out as the base current, typically very, very small, in the order of like microamps. Okay. And then the electrons are now minority carriers in the p-type base region. So if we reverse bias the collector base region, we say reverse current starts to flow. Technically, it's reverse current flowing, but we are now here. And the few holes that are there in the collector region cross over into the base and are swept through. Some of them will go into the emitter, the other ones go down into the base. So both holes and electrons contribute to the total current, both polar charges, hence bipolar. And then, since electrons are moving this direction, we say current is moving this direction, flowing out the emitter. And that's, well, that's how the magic of transistor operation. So let's take a pause, think over all of that. Let me know if you have any questions. Yes. Yes. The question being asked is from the base, are the electrons moving into the collector region? The answer is yes. Yes. So if the collector was negative, meaning if it was forward bias, from the beginning of its forward bias, then yes, it would not be. But the electrons would still be able to cross over from the base. So yeah, if you're applying, so there are two things to this. We apply DC voltage to set up bias at the three terminals, and then we apply AC voltage on top. Okay. So within those limits, if you apply DC voltage, if you forward bias both junctions, then yes, we would say that forward bias current is not flowing that way. So your question is, if this is minus and this is plus with respect to the junction, right? So yeah, the electrons would not be able to cross over that way. You had a follow-up question? Yeah. So because it's reverse bias, because the collector base junction is reverse bias. So there are minority carriers in the base, but because the base collector is reverse bias, they are pushed into the, and then the holes from there are now recombining over there. So okay, about 19 minutes left. All right, so each terminal of the transistor specializes in something. We spoke about that. In the diode, both the anode and cathode will conduct the current, and both can be said to be controlled by the externally applied voltage or the externally applied current, right? You change the voltage or change the current that you apply to the diode, and then the diode voltage and current changes. But you can't do it internally. You can't change anything internally. With the transistor, the collector is going to conduct a large amount of current. The base is going to control it, and the emitter both controls and conducts. Remember, current flows from the collector to the emitter in NPN. From PNP, it flows from the emitter to the collector, flips. But the base is what controls the flow of current. Okay. All right. So based on the connection of the transistor, there are three configurations we can use. Now, in a system, we'd have an input and an output. So a transistor being a three-terminal device, we can represent it like this. And you have a terminal that is common to both the input and output side. Okay. You have input coming in from the left, output collected on the right. So we would need a terminal that is common to both sides. If the collector is common to the input and output, we call it the common collector mode. If the base is common, then we call it the common base mode. And if the emitter is common, then we call it the common emitter mode. CE mode or common emitter mode is by far the most common configuration. Okay. So CE mode, meaning a CE amplifier, which is one of the configurations we look at in lab 3. Okay, that's one of the most common ones. Amplifier can be represented like this with a triangle. An amplifier is anything that amplifies either voltage or current or even power. So the transistor, the BJT amplifier, can be used in all three. Sometimes we have a need to amplify the current, but keep the voltage constant. Other times we would want to amplify the voltage, but keep the amplify the current, but keep the voltage constant. And other times we would want to increase both voltage and the current. Then we call it a power amplifier. Okay. So depending on that, we can use the configuration that we want. And CE is by far the most common because it amplifies both voltage and current. Gain of a system is simply the output or ratio of the output to the input. If the gain is greater than 1, we refer to the system as an amplifier. If the gain is less than 1, we call it a, what do we call it? Attenuator. So you saw attenuator in lab 2. We'll now look at an amplifier in lab 3. Yes. So the question being asked, it's an excellent question. I had a hard time understanding how and how it would work. So it's the question being asked is, if we apply a signal of AC signal of, let's say, 0.1 volt, how can suddenly magically become 10 volts at the output? Is it pulling something from the air? Well, can you answer the question yourself? Right? It comes from the DC biasing that we apply. So in general terms, so I would talk about this in the later slide, but I can talk about it now also. This is generic explanation. When we say amplifier, most of the time, not most of the time, almost every single time, we are referring to a system that is taking a small AC time varying signal and making it bigger. For instance, this microphone is capturing the sound of my voice. It's converting sound waves into electrical signals. Then it's wirelessly transmitting into computer. Then it's going into the internet via Zoom, which by itself, it's like an amazing delivery. Anyway, so inside that system, once the microphone sends it out, the signal would be weak. The sound waves are converted into electrical signal. Anytime you we do an energy conversion from one form to another, you would lose something, right? So we need to make it stronger, make it bigger, amplify it. Okay, so we have pre-amplifier stages, commonly known as preamp. You might have heard of guitar preamps, perhaps, because the signal coming from a guitar is it's even smaller. So we need to first increase the current, and then we increase the voltage. Okay, so preamplifiers and then amplifiers. So all of those come from a DC power. So we are amplifying the AC signal. The AC signals are very, very small, but we can apply DC signals of like 5 volts, 10 volts, 15 volts, 20 volts, 100 volts, 200 volts. And we can modulate the AC, we can modulate the DC with the AC signal. In the simplest of terms, I can express that the amplifier would take the AC signal. Let's say you have, this is of course not to scale. And this is some large DC value. What the amplifier is doing is it's taking the DC and it's giving it the shape of the AC waveform. And that is actually what happens. If you don't apply, you remember we talked about biasing, diode biasing the Q point. So if you don't apply any AC signal, you just apply DC, all you'd have at the output is the DC voltage. Okay, depending on the circuit configuration and everything. If you apply 10 volts DC, you might get 8 volts DC at the output. Okay, depending on the configuration. Some of it, of course, is lost in the biasing components across the resistors and everything. But you would get, like, let's say 8 volts DC at the output, flat line, nothing else. But now if you apply a very tiny AC voltage at the input, AC signal at the input, let's say like 10 millivolts or 50 millivolt signal, it's going to take that DC output, which is 8 volts, and now it's going to give it the shape of the 50 millivolt AC signal. And that's how we get amplification. Okay. Now, of course, everything that we just covered in one lecture is an entire class, like a fundamental semiconductor fundamentals by itself. Okay. So we're going to move on to see how we can apply it to a system. Yes. It does change. Yeah, it does change. So the question being asked is, when you have the different modes, operating modes, like common collector, common base, and common emitter, the operation would change a bit. But again, we are not, even in an EE class, we don't have sufficient time to actually delve into down into the semiconductor physics of what happens. We zoom in to the size of the atoms and subatomic level to look at the fundamental explanation, but then now we'll zoom out and then we look at how we can apply this device to circuits and systems. So there are many different configurations. Several of these configurations, whether it's common base, common collector, common emitter, will require biasing. Biasing is provided from DC supply voltages and resistors, right? We have resistors connected at the input and output terminals. So in this case, right here, we have, no, it's blurry. That's the input. And here it's common to both the input and output side. So it's common collector mode. On the next few slides, we have the common base, we have the common emitter. All of these we can simulate. Okay, but simulation doesn't capture everything that occurs in real life. Okay, so simulation, so the point of these slides are that you can simulate all of these and it will work in the simulation. But practically speaking, it's not going to work every single time. If you're lucky enough, it might work depending on circuit variables, but most of the time it's not going to work. There are many reasons why. One of the biggest is that we are applying an AC signal on top of the DC, right? The purpose of the DC is to set the operating point of that device, of the transistor, of the diode, of the MOSFET. We apply DC first. We prepare our device or prepare our system to accept the AC waveform. So the biasing is one of the most critical aspects of designing an amplifier because there are several different regions of operation when we look at the characteristics. And we look at all of this later on in this chapter. So one of the regions is known as the active region. And if we wish to use the transistor or the BJT as an amplifier, our biasing point must be in the middle of that active region, so that when the AC signal arrives, it does not go down, which is the region is known as cutoff, or it does not go up, which is known as the saturation region. So if it's in the middle of the active region, we can use the BJT as an amplifier. Cutoff and saturation put together, we can use as a switch for digital applications. So the BJT can be used as an amplifier. It can also be used as a switch, okay, electronic switch. Anyway, so the point was that we are setting the DC to bias our transistor, then we apply AC on top of that. So if you're applying AC and the circuit's not configured, meaning the AC should bypass the DC, then AC could end up blocking the DC. If it blocks the DC, then, or even if it affects it in a different manner that we intend, that Q point or the operating point is now shifted. So your transistor is operating in some region outside of your application. Okay, so it may not work as an amplifier. So that's one of the biggest reasons in all of these simulations and biasing circuits. Okay. Here we have the same thing here. It's a CB amplifier, works in SPICE, but it's impractical. If we struggle with it for hours, we might get lucky and get it to work in real life. But again, one of the biggest reasons again is the AC source may not allow the DC. And then CE amplifier, same thing. And we're going to look at a few of these configurations. We're going to look at a few of these configurations in lab 3. Okay, and this one is ground. So here's some better images of all 3 modes of operation. You have the CC, CB, and CE mode. If you look at the common collector mode, see the output's taken at the emitter. If you look at the CE mode, the output is taken at the collector. This is by far the most common mode. Even in the EE semiconductor class, we do 2 experiments. First is the DC biasing. We look at common base and common emitter mode. And in the next lab, we have them design a CE amplifier. Okay. And then you have the common base mode. And then, of course, we have cascade connections where you can have multiple transistors all cascading. The output of the first one is fed into the next one. The output of the second one is fed into the third. Third goes to fourth. So it's a multiple cascading connections. So biasing is basically choosing the supply voltage and choosing the resistor values so that our transistor operation falls within the active region. Okay, falls within the active region. And that's what our DC biasing is. Again, we want to look at these from a systems perspective. Right? How can we take this device and create amplifier systems and switching systems with this device? Okay, so in lab 3, this is what we're going to work with. Transistors are complicated devices. They're not, even diodes are complicated for that matter. But transistors, again, are complicated devices. So I wanted to cover at least one lecture before lab 3. And then next week, we'll look at a few diode circuits on Mondays and Wednesdays, and then wrap up diodes and continue with transistors on Friday. Okay. So, a couple of announcements. I posted about the Friday quiz earlier today. It's just, yeah, I was trying to implement it, but it's not like really a good implementation system. So I've decided to roll it into the Monday quizzes. So later on, if I do have the Friday quiz, maybe like 1 or 2 perhaps, but it'll be part of the entire quiz category. So if you've not yet read the announcement, please do so. And then Monday, we'll have the Monday quiz as usual. That will not be based on the BJT, that'll be based on the diode and the previous homework. So later this evening, later tonight, I will post an announcement about the Monday quiz. Okay, but just so I'm announcing in class, that Monday quiz will be regarding diodes, not regarding transistors. Yes. Friday, so let me understand. Time for Monday quiz.
Well, you said you moved the Friday quizzes.
Well, no, that's not what I meant. So the question we asked is about Friday or Monday quiz. No, I said Friday quizzes I'm not implementing. If I do give a Friday quiz, like maybe in week 5, week 6, week 7, maybe, I don't know yet right now. I have to spend quite a few days working on stuff to actually implement a good non-proctored quiz. But that would be like on a Friday or Saturday. That's it. It has nothing to do with the Monday quizzes. Okay, it has nothing to do with the Monday quizzes. Okay, yes. So the question being asked is, would the amplifier allow DC to appear at the output or not? Right? It will. DC will out. So at the output, we will have a DC component. So the DC component will show up as, you will have your waveform. So did everybody understand the question? Your waveform would be like this, where this would be at 0 volts. But the output of the BJT, you'd have something like this. And 0 would be somewhere here. So you'd have a DC component to that AC waveform. Think about what we did in lab 1. What was the second circuit? Anyone remember? It was a negative clamper. So clamper is a circuit that clamps your signal level at either a positive value or a negative value. So if you have an amplifier that has a DC component, you feed it into a speaker, which by the way, you can test it out. You can take a small speaker, it's connected to AA battery, and what you will hear is zzz, because it's a constant flat signal that's coming in. So if you take this signal with a DC component and give it to a speaker, you're gonna hear your music or your movie, but you're gonna have a buzzing noise in the background. So you give the signal to a negative clamper, and it'll push that signal down back to 0. Excellent question. So you'd have DC from the DC biasing, and we'll have AC. So you'll have both DC as well as AC, and then we can use different circuits to remove that DC component. All right, we'll end class here today, and we'll pick up here on Monday. Well, actually not here. And then I wanted to just point this out. If students are interested, maybe it might be too late for this year, but there are lots of national labs around. And this, I was attending a seminar from a postdoc scholar who was here today speaking about their work at Berkeley Lab. So this is Lawrence Berkeley Lab, LBL, and they have a lot of or ton of internship opportunities for undergraduate students. You can check it out at your own time. One of the internships that they have is a computer science summer program, computing something. But 2025, it's already filled up. But some of them might still be available. I don't know. So you might want to check it out. Okay. Summer undergraduate for internships. All right. Have a good weekend, and I will see you all on Monday.